Okay, so this is lecture 14, prep 2, and hopefully we will, I'll work through it in about 15 minutes, I hope. So I want to start with this example. So we have pure breeding parents. They have, the one parent is homozygous for two dominant alleles of two different genes. Remember what this dot means. It means we are not certain whether the genes are linked or not. We are doing these crosses to find that out. So we would write this notation differently if we knew the genes were linked or if we knew they were not linked. Okay, and this parent is homozygous recessive, so we produce dihybrids, individuals that are heterozygous for both genes, and we do the test cross. When we do a test cross like this, we only have to look at what's happening in this parent because the independent assortment and or the crossing over that we might be detecting are going to be relevant only in that one parent. We can't detect anything in this parent because they're just passing on recessive alleles to all the progeny. And so notice this notation, this just shows the phenotype. So we only put one allele to show the phenotypes. So when we look at the progeny, and we can consider these to tell us what the gametes were, right, in the F2. So homozygous, or not homozygous, dominant for both alleles, 140 of them, recessive for both, 135, dominant for the A but recessive for the B, 110, and the other way around, recessive for A and dominant for B, 115. So we see a difference here. If we're looking at, note which ones are the parental types. The parental types look like that P generation, the two dominants and the two recessives, and then these are the non-parental or the recombinant types. Now, 45% versus 55%, it's not that different. Sometimes, maybe if we collected thousands of progeny, we'd be closer to 50-50. Remember, Mendel had almost 10,000 P's in one of his experiments, and he still didn't quite have a 3-to-1 ratio. So, and these numbers are not so different that we can obviously say, well, independent assortment just isn't happening here, right? So this is where a statistical test is going to be of use. So we'll go through the chi-squared test, which is a way of calculating, whether the numbers you've collected or the observations you've made are consistent with the hypothesis, and then what you would expect to see if your hypothesis was correct, okay? And so what you're really asking is, how different are these numbers from the predicted ones? If they're not too different, then we will accept the hypothesis, the null hypothesis, which says that there isn't any difference. But if the variation is too much to accept that, then we would reject it, and we would have to say these numbers are not consistent, right? So you want a genetic hypothesis, and then you want to test it, and I'll give you an example in a second. And then you're comparing observed results with what you would expect based on a prediction. Okay, so how close is close enough is really what we're asking. Okay, so I want to go through each of these tables. So we had 500 progeny. In real experiments, of course, they never come out to exactly 500, but this is just, it makes the calculations a little bit easier to do. So we have a total of 500. Just think, if you did that cross with the dihybrid test cross, we expect a 1-to-1 to 1-to-1 ratio, which means we just divide 500 into 4 equal categories. So these numbers should be exactly the same. If you want to make sure you've done this calculation correctly, especially if the ratio isn't obvious, like 1-to-1 to 1-to-1, but is something else, add the numbers together and make sure that the totals come to the same. Commonest mistake is the numbers will be calculated and this number will be 480 or something instead of 500, which means something wasn't done correctly here. and therefore the number that's generated over here is way off, right? So you want to be really careful about that. If it comes out to a decimal, it doesn't here, but if it came out to a decimal, suppose the number was supposed to be 22.5, then you would put that as your expected value, even though you can't have half of a mouse or a fly or whatever it is the organism you're working with. But you've got to use the theoretical one with at least one decimal point, because if you start rounding up and rounding down, then your expected values are not going to be correct, right? If this is supposed to be a 1-to-1 to 1-to-1 ratio and it comes out as a decimal, you've got to include it. And etc. Okay, so that's really important. And you always use the actual numbers. You don't test proportions or percentages, and I'll show you why later on. So the first thing we do is we take the observed minus the expected. That's the first part of the calculation. And I always, even now, I've been doing these kinds of tests for years, but I always put it into a little table or a little scaffold because it helps me keep track of what I'm doing. It helps me make sure I've done my calculations correctly. So you take the observed minus the expected, in this case 15, in this case 10, in this case note minus 15, that minus is important, and in this case minus 10, right? When you add it up, it should come to 0, because if some of the numbers are higher than expected, the others should be the same proportion below the expected values. So another a good problem solver checks their work. Make sure the total adds up to the same total. Make sure the observed minus the expected add up to 0. Okay, and then you take the observed minus the expected squared, and so that's that number here. We square it in part. We get rid of any negative numbers because the magnitude of the difference is the same, whether it's a negative, if it's 15 off and a negative number, that's just as much off as being 15 over, right? So we make all those. Notice this isn't going to add up to 0 or anything. But then to correct it for sample size or adjust it so that the sample size makes a difference, we then divide by the expected, right? So the observed minus the expected squared, and then all divided by the expected. So there should be a line here. And so then you make a calculation for each of the categories that you're testing, and then you add it all up. So for the whole experiment, that's your chi-squared. And if I have done the calculations correctly here, the number should be 5.2, right? Okay, so that's the calculation. Note that when you do it in a table like this, you have a built-in place where you can just check that you're making your calculations correctly. And also, you put these categories separately, and you have the lines in the table so you don't forget a category, right? You make sure that you do chi-squareds for each of the categories that you're testing, and then you add them all together. So it's just a really good way of organizing your thoughts, organizing your problem solving. Okay. So you state a hypothesis. The hypothesis will be, in this case, that these observed data represent this ratio, 1-to-1 to 1-to-1, and the numbers we observe are different, deviate from, that's what it means. Deviate from means are different from the expected by random chance. So what this means is this is just a little random variation. The same way tossing, whatever that was, 500 coins would be. You're not going to get a perfect 250. It's going to vary a little bit. And then you do that calculation, which we did on the previous page. And then the next thing we do is we determine the degrees of freedom. So the degrees of freedom are calculated this way. You take the number of categories. Let me just change color here. You're going to take the number of categories and subtract 1. And the reason is, for your expected value, you could put anything you want in here. 100, 200, 50, even if it's not even based on anything that makes any sense. But once you've decided on expected values for these three, this one cannot be varied. because this adds up to 350 and the total has to add up to 500, so this has got to be 150. So you can change 3 of them, but after you've changed the 3 of them, the 4th one is not negotiable, let's just say. And so the degrees of freedom are going to be the categories. There are 4 different categories minus 1. That means you can vary 3 of these categories, but not the final one. Okay, and that's important for the calculations. And then you look at the table. This is a chi-square table. Some other mathematicians have gone to all the trouble of calculating in a case with 3 degrees of freedom, with a case of 5, you know, all the different probabilities of just numbers varying at random. And so the number that we calculated was 5.2, and it fits here on the table with the degrees of freedom as 3. Now the cutoff for analysis is 0.05. The p-values here are the probability of your the numbers that you've generated being as this different from the expected values. And so if you get a chi-squared here or beyond that to this side of it, as long as there's a 5% chance of getting this much variation by random variation, then we accept it. But if it's less than 5%, then we reject it, right? And you'll notice, look at the chi-squared values. The chi-squared values are really small. These numbers are very similar to what you predicted, and they get bigger as you move across the table. And in science, most of the time, we use this value as our cutoff, and we go, okay, we're willing to make a mistake 1 time out of 25% of the time, and we're going to have our cutoff line right here. Anything on this side of the line we're going to accept, and anything on that side of the line we're going to reject. Okay, yeah, and so our number actually falls here. It falls between a p-value of 0.1 and of 0.5, which means that there's between a 10 and a 50% chance that we could get numbers like the ones that we've generated just because of random chance. And that's pretty high. Well, this means out of every 2 experiments well, out of every 100 experiments you do, 50 would give you variation this much, right? So we will accept, in our case, we'll accept the hypothesis. The numbers that we've generated are close enough to the ones we expected that it is a 1-to-1-to-1-to-1 ratio that is just with a little bit of random variation. Okay, and as I said, the p-value sort of defines on how much error are you willing to accept. So the bigger your chi-squared value is, the less chance it is that this is just random chance. It means something else is going on. It's kind of like you toss toss a coin, I don't know, 2,000 times, and you get 1,700 heads and 300 tails. You know, you're going to have a chi-squared that's off the scale, and that will tell you there's something really wrong with those numbers. The smaller your chi-squared value that you've calculated, the more likely it is that this is really the ratio you think it is, and you are just seeing a little bit of chance variation, right? And so, and we set up, we could choose anything. We could say, okay, it has to be 0.5 or it has to be 0.7 or something before we accept it. But we have accepted in terms of science 0.05 as our general cutoff for analysis. There are sometimes experiments where they change it a little bit, but this is standard. And so basically, there's a 5% chance that you're going to see this kind of variation, the same or more, right? And so the kind of mistake that we will make, though, we're not 100% sure. 5% of the time, we would reject our hypothesis, even though it was correct. And so that's what we accept. In order to be fair, conservative enough, we accept that we will sometimes reject a hypothesis that's correct. And hopefully that's clear, but you can definitely ask about it. So in our case, we can't reject that null hypothesis, and so we can conclude that the numbers we have are consistent with the fact that those two genes are on different chromosomes. And just notice, this doesn't really necessarily mean that we're correct in our hypothesis, but what it means is the data we've generated don't let us disprove our hypothesis. Okay, and if the idea of probabilities and errors and all that kind of thing is just really confusing, and you don't really imagine that you're going to have to do much statistics in your future, if you just remember this, that this is our cutoff, and everything on this side with the lower chi-squared values, we accept the null hypothesis, and if it's on this side, we reject, then that will be good enough. That will be enough for getting through this class. Okay. And I just want to point out that the larger the sample sizes, the more accurate we can really be. And so suppose we had 5,000 progeny instead of 500. The numbers we have generated are larger, and the chi-square value that we calculate is larger. And so if we collected more progeny in our experiment, we might actually conclude, and the same pattern was observed, then we might conclude that, oh, we have to reject this. This is not, these are not numbers that we would expect to see. They're not close enough to what we predict. There's something else happening. Maybe these genes actually are on the same chromosome or something. We'd have to do some more investigation, right? So we would reject that null hypothesis. Okay, and that's why, and I said this at the beginning, but that's why you can't use a percentage or a proportion, because it takes away the effect of that sample size, and it makes a difference. You know, these numbers are proportionately exactly the same in the other experiment, but our outcome and what we conclude is different. And so you've got to always use the numbers, not the percentages or proportions. Oh, I made a mistake here. That should be chi-squared analysis. I knew I had not found one of them and corrected it. So I'm going to stop there. Now, if you would like, I'm going to make a third video, and it will just go through one more example. And if you feel like going through it again will be helpful to you, then you can do that. If you feel like you've kind of got it and you know what you have to do, then I would consider the third prep to be optional. Yeah, but I'm going to make it available for those of you who may feel you need it.